KEET TV presents Homework Hotline, the after-school show that fuses learning with fun. Watch local teachers bring the classroom on air and online. This is Homework Hotline.
Hi, welcome to Homework Hotline. My name is Dan Scofield. I teach science at St. Bernard's Academy.
And my name is Rita McConnaughy, and I'm a math specialist with Northern United Humboldt Charter School. And you're watching Homework Hotline.
Yeah.
Thank you for coming.
Yeah, welcome to Homework Hotline. We're glad that you are tuning into us today. And I want to talk to you about something and do some experiments with something called Centripetal Force.
Awesome.
We played around with this about a year ago, and I want to kind of continue on our exploration of it, and we'll look at some really cool things about it that you can find out about using this. Just thought exercises and things that we can actually observe.
Awesome.
And we'll kind of end with the last year's Nobel Prize winners in physics, which is really great. Anyway, so centripetal force is the force that keeps things spinning.
All
so
right.
Centripetal force is what keeps things spinning. So when I spin something around like this ball, the reason why I could spin it is that I'm causing it, I'm pulling it from the center. So the ball is always moving, it's always accelerating towards the center. At any point it's accelerating towards the center. If I was to let it go, if I was to let it go like right there, I'd probably hit Rita in the head.
Oh, that wouldn't
so I
be
won't
good.
do that. Or if I let it go right there, it'd go flying out in front of me. But it's always moving. At any given moment, it's always moving in like tangent to the direction it's spinning. So right there, it's moving that way. Right there, it's moving that way.
Gotcha.
Towards Rita. And right here, it's like moving towards my head. So, but what gets it to go is this force going towards the center. And the reason why you know that's the case is that if I let go of it, there's not a force going outwards, because otherwise you just go flying outwards that way. If I let go, anytime you let go of it, you go flying off to the side. And so to keep things spinning in a circle, you have to have that force kind of going inward, and that's called centripetal force. You can do some fun things with it too, like centripetal force. I can get this to spin. If anybody's been on a carnival ride where they spin around in a circle, they stay on the ride.
Wait, you want to spin water in a circle?
I'm going to spin water in a circle.
Are you going to go like vertical in front of you or like horizontal?
I could do both. I think horizontal might be a little crazy. You probably get
Because then
it
it'd
everywhere.
really be a shower if you go horizontal.
Yeah,
Above your
I mean,
head
I could try it.
horizontally. Well, let's try the vertical
I'll
first.
try the vertical. I'll try the vertical first, and so I'm going to spin it and get it to be upside down.
Okay.
And so I'm getting it to spin in a circle by applying a centripetal force towards the center.
Okay.
We'll have to think about why the water doesn't come flying out at the top, if it doesn't, or the cup goes
Okay.
flying off at the top. I'm going to move out to the front so I don't spray everything.
Is there anything special about the platform it's on?
I just tried to make it flat.
Is the cup attached to it at least? The cup's not even attached to it.
Yes.
Okay.
Okay, we'll show that. Not attached. Not attached. Nothing special with the water. It's not ice.
Okay.
All right.
It's not like fake looking water.
Well,
Actually slime. or
okay, so
something.
here we go. Not
Okay.
slime. So we'll see. Here we go.
Wow.
We'll go twice.
Wow.
Maybe 3
no
times.
water coming out.
Let's see if I can
That's
go side to
amazing.
side. Ready?
Okay.
I'll kind of move to side to side.
Oh, okay. Holy cow. No shower for Mr. Scofield.
All right. So
That's amazing.
why does it? It stays in the. I get it to go in a circle because I apply a centripetal force towards the center. But the reason why it doesn't come flying out of there is actually due to just the inertia that the water is continuing to go in the direction it's going. It stays on the platform because there's this normal force pulling down. It's really equal to that centripetal force that's pulling down. So it's pushing it against the cup, and the water's just continuing to go in the direction that it was going before, which is kind of against the sides of the cup, so it never really comes down.
Cool.
If I slow down enough at the top,
If you wouldn't go fast
would-
enough, then the
yeah,
inertia
yeah.
of the water wouldn't be enough or something.
right, if I slowed down enough, then I think it wouldn't go over the top. You can kind of figure out how much that has to be in order to overcome gravity. But those are some fun things you can do. You can spin a bucket that way, and the reason why it doesn't come out is because of that inertia, the inertial motion of the water in the cup. It's still pressing against the sides, and so it's not going to fall down.
Cool.
Anyway, yeah, it's cool. And so you can do all kinds of things with that. One of the other things, too, is you can set something up in equilibrium where I can spin this stopper, and I have a weight attached to this end. I've got a little glass tube here, and then I have mass hanging from this. And so if I spin this fast enough and not hit Rita in the head again, it'll hold up the mass. All right. So right now it's holding up the mass, and I'm trying to keep it exactly at one spot. And so if I let it go and I don't spin it anymore, see how it drops?
Starts to slide.
It slowly slides down. And see how it's spinning faster and faster and faster and faster. It gets stopped. So there's this relationship between how fast this thing spins. So if it's shorter,
try it again.
in order to get it to stay up the top, in order to stay up there, I have to spin it faster, right? Mm-hmm. Because that radius is smaller.
Is that kind of like a helicopter type of motion?
Right. I guess if I had bigger blades on a helicopter, I wouldn't have to spin them as fast, would I? In order for it to get lift. But the balance here, it stays in equilibrium. It stays balanced.
So this little rubber one is a lot lighter than this. Is this like 2 kilograms or?
That's 0.2 kilograms.
0.2 kilograms.
0.2 kilograms. And so we can represent that balance by knowing that the forces are going to be equal. So I know that I know that the forces, the centripetal force that I'm applying by the stopper is equal to the gravitational force on the mass, because it's not going anywhere. It's just staying in one place. And so I could figure out what that should be doing a little math. Let's do some math.
Okay.
All right. So the math that we're dealing with is, of course, centripetal force is I use like capital F for force, and I usually put a little subcharacter for C for centripetal force, right?
Okay.
So that I know that force is going to have to equal the gravitational force of the weight pulling it down, right?
Okay.
Well, the gravitational force applied by the weight is equal to the gravity between it and Earth.
Okay.
Which is equal to, we say just mass of the
object.
The object. We'll say the mass of the mass, or the mass of the weight. We'll
okay. Mass of the weight. So MW.
MW times gravity, and the gravitational acceleration. Oh my goodness! I'm going to have to use the pen.
Yeah.
And then centripetal force is equal to is this.
Other side of it, I think.
Yeah, it's going to be over here.
The weight. Oh yeah. Go.
Yeah, it's going to be equal to the mass times acceleration, and the mass in this case is the mass of the stopper times that acceleration of the centripetal acceleration right there. But I know that acceleration, centripetal acceleration, is equal to v squared, which is the velocity of the stopper. Oops. So it's m, mass of the stopper, over the velocity of the stopper. So it's v squared over r.
And
then
r,
the radius is the distance from the stopper to the center.
Okay.
Okay. And so now I can figure out what that velocity should be by just doing a little algebra. Right? I mean, if you want to solve,
I can put it over here.
Can you solve for v squared?
Okay, so the mass of the stopper is
mass. We'll just keep that in. We can just solve for.
Do you know the number?
I do know the number, but I'm just going to just solve for the.
So m sub s, and then we want to solve for v.
Yeah, we'll solve for v, but it's
the velocity squared, and the radius.
We'll plug all the numbers in a second, but we can get. I know the radius is actually 0.5 meter, but.
Okay, and then do I need the other side of the equation as well?
Yeah, you should put the other side in.
Okay, so mass of the weight times the gravity gravitational pull on the Earth, right?
Yeah, gravitational, of objects near the Earth.
Near the surface.
Yes, yes.
Okay. Doesn't matter if we're like up on top of a mountain.
Doesn't matter much. It doesn't even matter. You can be several miles
We fluctuate the tiniest a bit, but
yes, not much at all.
Not enough to change an equation necessarily.
No.
Okay. So do we need a table of values when we're going
No,
through
we
this?
can get all these things.
Okay.
Actually, the gravitational pull of the Earth is 9.8 meters per second squared. We can just round that to 10 if we want to. And then
Sure. Well, I'll put 9.8 for right now.
And then the mass of the weight is 0.2 kilograms, and we're going to use that.
Kilograms, sorry.
Yeah, 0.2. And then we don't know what the velocity is, but we do know the mass of the stopper.
Do you think I should fit in here kilograms?
Sure, we can put units in there.
And I'm using a dot for multiplying. So, okay. And then on the other side?
Then the mass of the stopper was 20 grams, which is 0.02 kilograms.
So we want to go 20 grams and change it to kilograms.
So we got to divide by 1,000.
Right. So a decimal point gets moved over 3 places. So 0.02.
Yep. 0.02. Yeah, good.
2 kilograms.
And that's kilograms.
Okay, times velocity, but that's our unknown,
Yeah,
right?
So,
So
times
I'm
velocity, keep it
leave
squared.
it as v squared.
And then divided by, and now as long as I keep this tape right here, the radius of rotation is 0.5 meters. Yep, it's still there. So as long as I keep it there, it's 0.5 meters.
0.5?
Mm-hmm.
Okay. So are we gonna, this meter on the bottom will be okay with this meter on the top over
well, we
here
should end
eventually?
up with, our answer should end up with as meters squared, second squared. Velocity squared equals meter squared, second squared.
Okay.
If you multiply both sides by 0.5 and divide both sides by 0.02.
Okay, can I grab a calculator for this?
Sure.
That'd be okay?
Yeah.
Okay.
You want me to do the calculating? You can.
Either way.
All right.
So if you have it handy.
I do have it handy. Okay. So v squared is going to equal. So we do 0.2.
So to get rid of dividing by 0.5, we're going to multiply each side by 0.5.
Right. And
to undo multiplying by 0.02, we're going to divide each side by 0.02.
So divided by 0.02. Then we get. Oh, this is pretty hilarious what we get.
What is it?
I didn't actually work this out. So we get 49 meters squared, second squared.
Exactly?
Exactly.
Wow, that's pretty awesome. So meters squared per second squared. Sometimes it's hard to know whether it's a label, like a unit of measure, or if it's a variable.
Right, right.
So,
So when we divide by meters squared, second squared, the reason why I laughed is because 49 we know it's not just a square, it's a perfect square.
oh, it's a perfect square, right? Because we
So-
have velocities to the second power.
So we.
So to undo squaring, you take the square root of
Right.
each side.
So we take the square root of each side, and so we're going to get.
See how a math teacher can get excited about the
Oh,
math?
yeah.
I didn't even.
When I turned 49, that's what I told my class.
Oh, you're a perfect square.
I'm not just a square, I'm a perfect square. So
I love it.
so
Okay.
and that means that velocity is going to equal.
So those two undo each other. Just v, so velocity equals 7 meters per second, meters squared.
No, that
Oh,
it
no,
undoes
no,
the units
no,
too.
the units are oh,
Isn't that
how
great? So
exciting.
it should be, okay, so when I do this, and now this is where the fun part, this is where the science comes in, is this is our theoretical velocity, is 7 meters per second.
Okay.
All right, so let's see if we actually get that. And so,
Could I ask what velocity is, just for those
velocity
who
is
may not
is
know?
the distance something goes over the time it goes. So it could be, I don't know,
Similar to
miles per second. It
Similar
could be,
to speed,
yes,
right? But it shows the direction.
correct. And so
Okay, awesome.
acceleration is a change in velocity, and velocity has a direction. The speed of the stopper isn't going to change any, but the direction changes, and so it accelerates because it has a change in direction.
Because
Now,
it's going around.
It's going
in a
around. So it's
circle.
constantly changing direction, so it's accelerating.
Okay.
And so what we need to do here is collect a little data.
Okay.
And so I'm going to set the stopwatch up, and we're going to see how fast this is actually going, and see if it actually is going 7 meters a second.
Okay.
And so we'll do this.
Do I need more room to work?
We might, just maybe put down.
Because I can add another sheet if that works.
All right, so we already know it's supposed to be 7 meters a second.
7 meters per second.
So what I'm going to do is start the clock, and I'm going to count rotations.
Okay.
And then you just tell me when you want to start, and then just count up to, I don't know, take 20
seconds?
Or we can just do 10 seconds. That'll be close enough.
10 seconds, okay.
Okay, so when you say start, I'm going to start counting every time it goes around. I'm going to get it going here so it's in equilibrium. And you just say start.
Start.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4.
Stop.
Okay, I got 25.
25. So that was seconds and rotations.
Now, if we have more time, we want to do a bunch of trials of this. But we're just going to go with the one.
So 10 seconds, and you said 21 rotations.
25 rotations.
25. Okay.
So now we know that means it took, for each period of time, it took 25 divided by 10. So it's going to be, 10 divided by 25. Sorry about that.
Oh, seconds per rotation?
Seconds per rotation. And so 10 divided by 25, I almost did a mistake right there. Because 10 divided by 25, and so it did 0.4. It's 0.4 seconds per rotation. And that would be we just call it, its period of rotation is 0.4. And so if we can get its velocity by figuring out how far it went, because you know how long it takes, but how far did it go? And this, I think, might lead to something that Rita was talking to last time.
Period of rotation, you did 10 divided by 25, and you said 0.4.
So it's 0.4 seconds per rotation. And so how far did it go? Well, we can figure that out. We're going to assume that it went in a circle, and we love circles in math. And so the distance it went in that rotation was equal to 2 pi.
2 times around?
2 pi times the radius, right? Or pi times the diameter. And so since its radius was 0.5 meters,
okay.
so it went pi. This is.
I need to write this
So
down.
write it down.
Okay.
It's distance. So velocity is distance divided by time. We get the time.
So velocity equals d for distance divided by t for time.
Correct.
Okay.
Yeah, that's good. And the distance is 2 pi r.
2 pi r because it went around the circumference of the circle.
Yeah.
Okay. So velocity equals 2, and not like pumpkin pie, but like the number pi, 3.14159,265, but we often just use 3.14 or just leave it as pi. Can we do that for a little bit? And then times the radius, which was 0.5 meters?
Yeah, it was 0.5 meters.
Okay, thank you. I don't know why I'm putting a 0 in there for 0.5, but there. Okay, and then divided by the time, which is 0.4, right? Should we get 7 if we do this?
I think we're going, I don't know. I mean, we should.
Oh man, we should get 7 if we did the math right.
So I'm going to use 3.14 for pi, and I'm going to multiply it by 2, and then I'm going to multiply it by 0.5.
Okay.
And that equals that, and divide it by 0.4.
Okay.
And I get 7.85.
Ooh, what did we do wrong then?
Well, so V equals 7.9. That's what we got.
Okay, so but
that's not bad.
Is that because of our experiment here? Maybe it wasn't exactly 10 seconds and exactly 25 rotations.
Maybe. And so if we were writing this up as your lab write-up, you'd say maybe I didn't, we didn't get the right number of counts. Maybe I didn't measure completely correctly on it. But I mean, we're within.
I think sometimes that important part or the important piece isn't always just the answer,
right?
But it's the process to get to the answer.
Right.
You know.
That's pretty close. That's not too bad.
Not too bad.
Not too bad.
So we calculated it as 7.
Yeah, the theoretical was 7, and we ended up getting the actual being
Okay.
7.9
I like
meters
that
a
word
second.
too. The theoretical
Right,
number.
right. We should
In
have-
theory, it should be this, but our actual is what we got was 7.9. Okay.
Cool.
And meters per second?
Meters per second, right.
Thank you.
So we can think about centripetal acceleration, centripetal force, something keeping something in orbit, or something keeping something spinning around. Newton thought about this, and he had a thought experiment saying, okay, so he knew that the gravity pulled things to the ground, close to the ground, and he looked at the moon and thought, well, I wonder if the same force pulling things to the ground close to Earth or pulling things around the Earth in the same way.
Oh.
And he was able to figure that out. And they knew how far away the moon was back then. They knew how long it took to go around. They knew, and they knew, that as well. And so he calculated, by using something similar, he calculated the acceleration of the moon around the Earth.
Wow.
And he thought about things close to the Earth, and he was saying that, well, the moon is about 60 times farther away from the center of the Earth than things on the top of the Earth, just on the surface of the Earth. So it was 60 times as far away from the radius, the center of the Earth, to the moon. And when he calculated the acceleration of it, he found out the acceleration of it going around the Earth was 3,600 times less than the things on the surface of the Earth. So 60 to 3,600. And so he made that leap to say, oh, it's distance squared. It's an inverse of distance squared. So 60 squared is 3,600. And so he figured out that that gravitational force that accelerates things gets less and less and less by the distance squared.
Is this the ratio?
Yeah, that was the ratio. And so 60 squared is 3,600. So he put together this very famous equation.
3,600, same as 60 to the second power, 60 times 60. So the distance squared to the distance, right?
Yeah, so it was that. So you take 60 squared, the distance. And so he knew that the gravitational force from this gravitational force is proportional. I should have said, but it's somehow equal to something over the distance squared. And he also reasoned, because of what Galileo did before him, saying that objects have the same acceleration no matter what size they are. All right? Oh. So where the big things and little things near the surface of the Earth accelerated the same. And so it didn't matter what they were. It just means they knew that relation, but that the force as things got bigger must be greater in proportion to the size of things. And so they also knew that means that the mass of one thing times the mass of another thing. So that means if I double the mass, that means it takes double the force, and you get the same acceleration. Okay. So you knew that. And then he knew this relationship existed, but he didn't know exactly what the numbers were because he didn't really know what the mass of the Earth was. Mm-hmm. It took another person later on to figure that out.
It's a little hard to weigh the Earth.
That's right. It's hard to weigh the Earth. You can weigh smaller things, but this is based on this gravitational constant that always stays the same no matter where you are. Was the case. So this is a very famous equation about universal gravitation. He didn't know what G was. It took a while for people to figure out what G was, but now they figured it out later on.
Gravitational pull?
It's the gravitational constant, and it's a really, really small number. It's 6.67 times 10 to the negative 11th.
Oh my goodness, that's really
So it's really small. So that means this force is really small. Like the gravitational attraction between me and you is pretty small. But as things get bigger, as one of these masses gets bigger, it gets greater. Okay. And what we can do with this kind of thing, by using this and a couple other manipulations, you can find out what the mass of any object in the universe is as long as you see something rotating around it. If you see something rotating around it, you know how long it takes to rotate, and you know how far away that object is from the center. You can figure out how massive that thing is that's rotating around it. So
that's how you figured out the mass of the Earth?
Well, you can, by the satellites. Yes, by the satellites going around it, you can figure out the mass of it. I had a picture of Europa and Jupiter to figure that out, but this is going to take a little while. But this is a great picture taken by Hubble, and it shows Europa, which is a little bit smaller than the moon.
Really little moon?
And it's about the size of our moon. a little bit smaller, going around Jupiter. And if I told you the numbers for that, you could figure out the mass of Jupiter, and you get really close. You can get within 10% of it. But the really fun thing you can do is if you look in the constellation Sagittarius, which is kind of in the southern sky, you can see a bunch of stars there, and that pretty much is right towards the center of the galaxy.
Wow.
And researchers over about a 20-year period, they took an image that we can show up here right now of track the stars that are going around the center of the galaxy. And if you look at, there's one right in the middle there, that's kind of whipping around there. That's over 16 years. That star is called S2, kind of right in the center. You see how it's going around?
Uh-huh.
That does a rotation about every 16 years. Its radius of rotation, that means on average, see how it's an ellipse, so it's not exactly a circle. So you want to take maybe average radius is about...
Is it just replaying over and over?
Yeah, this is replaying over and over again. So and these are actual tracked images of the stars themselves. So right near the center. But you see how it's going around? Something like that?
Yep.
And well, it's going around something that's right in the center of the Milky Way.
Wow.
Right in the middle of the galaxy. That they're all kind of rotating around this thing, and that one in the center is the star of the show, because they could figure out how far away it was on average, and just from the web, I got the numbers. I didn't kind of look up what their values were, but just from the values, I got the radius of rotation is about 1.4 times 10 to the 14th meters. So we can, as long as we use meters, right?
Okay.
And its time of rotation is about 16 years. And so if we want to use meters per second, that, for those of you at home, that's 500 million seconds. So 16 years is about 500 million seconds, right?
Okay, these are big numbers.
And then, so as long as you plug those values in and it ends up being, if you say, take 4 pi squared radius of rotation cubed and divide that by that universal constant g and period squared, you can get the mass of the thing that's going around.
So this G is universal, not just Earth, but it's...
And that's one of the big assumptions physicists make, is that
it's universal.
Is that they have to make the things in the other side of the universe work the same way as things here. But that is an assumption, right?
Yep.
We have to assume that that's true. But if you plug all those numbers in, and again, if you want to play from home, that's what you can do. Is that I use 1.4 times 10 to the 14th meters. And the period of rotation is 16 years, about 500 million seconds. You get if you plug that into that universal gravitation kind of solved for this, you get that the mass of whatever that thing's going around is about 3 million times the mass of the sun.
Wow, our sun. That's amazing.
So it really is about 5 million. Anyway.
Mind blowing. Thank you for all the fun math. Physics, right?
Yep, all physics.
Cool.